to data management. Then we're going to discuss the elements of a database system. Those elements are a data model, schemes and instances, the three-stream architecture. We're going to talk about the crucial role of a data dictionary or a catalog, and we're going to discuss some DBMS languages. We're going to briefly touch upon SQL, which is a very important database language that we're going to discuss very extensively later on. We're going to conclude the chapter by discussing some of the advantages of database design. Applications of database technology. Well, if you look at today's business environment, databases all are over the place. Think about a banking setting, for example. Banks are going to collect information about their customers and every transaction they make. So as soon as a customer makes a payment with the bank, applies for credit, or is going to buy or sell some securities like stocks, all of the information that is related to the transaction will be stored into a database. That could be customer information, like customer name, date of birth, gender, income, marital status, address. It could also be transaction information, like type of credit, amount of credit, duration of the credit, maybe also a measure of creditworthiness of the customer, etc. So all of that information needs to be stored. Also think about a supermarket setting, for example. Supermarkets want to know what products are being purchased by which customers, when they're being purchased, where they're being purchased, and in what quantities. So you see, those are two very popular applications of database technology, and they involve the storage and retrieval of different types of data. The data could be traditional, numeric, and alphanumeric. That means just numbers, letters, characters. But it could also be multimedia data. Imagine that the customer makes a call to your firm and has an inquiry about specific types of products or services, or maybe even files a complaint. Then what happens is that you want to store the audio of the call and connect it to the customer. Maybe you have some videos of your customers that you want to also digitally store. Maybe you have some images of your customers. Maybe you have some fingerprints of your customers. So it need not only be traditional numeric and alphanumeric data, but it could also be any type of multimedia data. A very popular example of a video database application is, of course, YouTube. YouTube stores a tremendous amount of videos. It keeps the videos itself, but also all kinds of information related to the video, like the title of the video, maybe a short abstract or description of the video, maybe some ratings, reviews provided by users, etc. Using database technology, you can also monitor data and autonomously take action when that is required. Think about a stock replenishment system, for example. A stock replenishment system is going to keep track of stock levels, and as soon as the stock level drops below a minimum required value, automatic orders will be placed. All of that can be fully automated using database technology. In a web environment, databases can also be successfully adopted. Databases can be used to store HTML, hypertext markup language information. HTML is a standard which is going to focus on the representation of web documents. Databases can be used to store information into PDF documents. You can have a PDF document that actually has a product description or any kind of product information, and that you also wish to store in your database application. It could also be used to store images, XML-based documents, and so on. In a supermarket setting, you can sometimes have really huge databases. Think about Walmart. Walmart is probably the biggest supermarket in the world. It's an American supermarket. And it's going to store information about all the products that it sells together with all the transactions themselves. Walmart recently decided to also invest into RFID technology, which stands for radio frequency identification. That means that all the Walmart products, instead of barcodes, will be equipped with small antennas. Small antennas that will allow the products to communicate with the database application by means of transceivers built into the roof of the supermarket. That means the database application can continuously monitor where the products are, in what quantities there are, what products tend to pass their expiry date, etc. So this generates a tremendous amount of data, and given the size of it, one typically no longer speaks about databases, but about data warehouses. So data warehouses are typically very large-scale, huge databases with different terabytes or even more of data being collected, sometimes even on a daily basis. Let's look at some definitions now. So a database is a collection of interrelated data. What do we mean with interrelated data? Well, this is data with relationships between the various concepts underlying the data. Think about a university application, for example. So in a university application, you can have different information concepts, like you have an information concept of student, you have a concept of a professor, a course, and a building. Now, between those information concepts, you have relationships that exist. A student can take courses, a course can be followed by students. A professor teaches courses, a course is taught by one or more professors. A course takes place in a building. In a building, multiple courses can take place. So you have the data items, the concepts or the objects themselves, student, professor, course, building, and then you have the relationships between them. Well, a database is going to collect both. And it's going to represent some aspects or a subset of the real world, the universe of this course. The universe of this course is the problem setting in which we are working. That could be the university administration, for example. You want to build a system for a university administration. A database is logically coherent. That means all the information items are connected. Students, courses, professors, etc. And it has some inherent meaning. It is meaningful in a particular setting. It also has an intended group of users and applications. So you're going to have different users. You're going to have users like students, which are going to make use of the university administration system just to see what courses they can take or just to register for certain courses, for example. You can have professors that are going to use the university database just to find out what students are subscribed to their courses, how many students, etc. You can have educational program assistants that are going to help students configuring their ISP, individual study program, etc. So you have different types of users and applications. And of course, a database should be appropriately managed. And the way it can be managed is by means of a database management system, or DBMS. And that's a collection of programs, software in other words, that will enable us to create and maintain a database. It will allow us to define, maintain, and monitor a database. So it's like a general purpose software system that is going to facilitate the process of defining databases, but also constructing and manipulating databases. When we say manipulating databases, we mean that it will allow us to insert new information into the database, register new students, for example. It will also allow us to update information into the database, update the marks of a student, for example, or it will also allow us to remove information from the database, for example, removing a course which is no longer offered. So that's a DBMS. It's a collection of software programs that will allow us to do that. A database system is then the combination of both. So it's the combination of the database together with the DBMS, the database management system, software or system. Let's take a step back in time and let's see how approaches towards managing, storing data historically developed. Well, the first approach towards dealing, storing, and managing data is the file-based approach. And that was an approach that was very common in the 60s to 70s of the previous century. Here you can see an example. So imagine we have a couple of departments in a company setting, each with their own application. So we have an invoicing application, we have a CRM application. CRM stands for Customer Relationship Management. It's an application that allows you to manage the customer relationships, understand the needs of the customers, understand interests of the customers, etc. And we have a GIS application. GIS stands for Geographical Information System. A very simple example of a GIS application could be an application that is simply going to figure out where most of your customers live, for example, or where they make their purchases, right? Very, very important information to know. Each of them need data. Of course they do. And the data is being stored into separate files. So you can see 3 separate files here, each storing the data needed for that one particular application. Very important to note is that those files are clearly not integrated. They're separate. And if you have a closer look at some of these files, you see a lot of replication. So you see customer number being recorded here, here, here. similar to customer name. Of course, each of these files also contains specific information for the application. So here you're going to have VAT code, you're going to have turnover, and zip code, for example. But what is really worrying is the replication or the duplicate data, because that could create all kinds of issues. Duplicate data can very easily lead up to inconsistencies. Imagine that you would change the customer number here. Imagine that your customer base grows substantially and that you want to change the customer number such that it has more digits now because you have more customers. That would mean, in order to make the connection to the other files, that you would have to change it here, you would have to change it there, and then also change the definitions in each of the applications. So it's going to involve a lot of changes that may easily be forgotten. And if they are forgotten, they have very dramatic impact because it means you have bad data of bad quality, which is no longer well integrated. So you see, this file-based approach to data management has a lot of disadvantages that come with it. It has a lot of problems. Let's zoom into some of the problems into a little bit more detail. Well, the first problem relates to accessing the data. If you want to access specific data elements, that means querying your database or your data, then in a file-based approach, you have to manually program your queries. Here you can see a query, find person, which is going to take the name of a customer as input. And basically, you have to program a small do loop, which is going to actually iterate through each of the lines of the file just to find that one particular person that you're looking for. This is in the file-based approach. So if you have a query, if you want to find particular information, then you have to program it. And of course, it becomes a lot more difficult if you would need information which is stored in different files, because then in your program, you would have to store or you would have to access those different files, bring the data into some kind of staging area, aggregate it, and then make sure that you report the result of the query as desired. So it becomes a very cumbersome exercise to query multiple files simultaneously. This is totally opposed to the database approach. In the database approach, everything will be stored in a database, and the DBMS will foresee DBMS languages to query, manipulate the database. And one of these languages is SQL. SQL stands for Structured Query Language, and just analyze the abbreviation. It's a query language which is structured, so it has certain kind of built-in structure that allows you to formulate your queries in a very user-friendly and effective way. Here you can see an example of a query. Select from the people database where the name is, the particular input name you're looking for. This is a very transparent, efficient way of working with databases. It basically only declares what you need. You no longer have to manually program your query, which was the case in the file-based approach, but you just declare what you want. SQL, as such, is declarative. You declare what you want, and the system will work it out for you, which is really nice, which is really very user-friendly. The file-based approach contains a lot of storage waste, lots of wasted storage space because of duplicates, redundant data. So you have customer number, customer name, remember the previous example, which is being stored in different places. So if you're going to have lots of customers, that will involve lots of duplication of customer numbers and customer names, which is not very nice. So also, if you're going to change your customer data in one file, you will need to change it in all the other files, and you will also need to change the definitions in each of the programs, which is again not very nice. We also have a very strong dependency between applications and data. As I said, the change in the data definition necessitates changes in all applications that use the data. Also, integration becomes very important, so very difficult actually if you want, because in the file-based approach, the information is spread out across different files. So remember the example I gave earlier, in which you want to find information which is contained in those different files. Then you have to access all those files, bring it all together, consolidate the data based upon customer number, etc. So it becomes a very tedious exercise to work out. So it's going to come with really high difficulty, high cost, and maybe the results will not be that very accurate. Let's now contrast the database approach to data management with the file-based approach to data management. In the database approach, the DBMS is going to contain both the data and a description of the database structure and constraints. Database structure and constraints, what do we mean with that? With that, we mean metadata. Remember the university application I discussed earlier. So there we had all kinds of information elements, students, professors, courses, buildings. Well, with metadata, we mean data about data. So we're going to clearly define what kind of information we want to store about professors. We want to store professor number, professor name, professor gender, date of birth, etc. Likewise for student, likewise for course, likewise for building. We also want to define the relationships between all those data elements. A student can follow courses, a course can be followed by students. A professor can teach courses, a course is taught by professors. So these are examples of database structure and constraints that should all be stored as metadata in the catalog. The catalog is the heart of the database application, since it contains all this metadata. It contains the data definitions and the data descriptions. We don't have a catalog in a file-based approach. In a file-based approach, only the data is stored in a file, and the structure of the data definitions, are being stored in the applications that will access the file. So that means that you have a lot of duplication of data on the one hand, but a lot of duplication of data definitions on the other hand as well. In the database approach, if you change some of these data definitions, if you change the structure of the DBMS, it only requires updating the information into the catalog. So we can directly update data definitions in the catalog. We don't need to update the applications in any way. So we have program data independence. We have a very loosely coupled architecture there between the programs and the data, which is very sophisticated and which is very nice. This is as opposed to the file-based approach of data management. In the file-based approach, we have not loosely coupled architecture, but a tightly coupled architecture. Programs and data are very dependent. One program is going to access one particular data file, so we have a situation in which changing the structure of a file would require changing every application that is going to access it. In a database approach, we can also have different views over a subset of the data, right? So imagine, again, the university application. So in the university application, we can have, for example, professors, which are only interested in a subset of the information. We can have students, which are only interested in course information, for example. We can have educational program assistants, which are only interested in certain piece of information. So using views, we can actually select the subset of information of particular interest to a particular user, to a particular application, and offer it to them as such. So a view is basically a subset of your database tailored towards the needs or the activities of a particular set of users or applications. The nice thing about the DBMS approach or the database approach is that those views can be defined, stored in the catalog, and then subsequently used. We don't have that in the file-based approach. In the file-based approach, if you would like to define views, it would require copying files, it would require copying parts of files, and any changes made to those duplicates should be carefully merged in all the other duplicates. Databases are also more and more used in a distributed environment. Databases will typically become more and more accessible in a World Wide Web environment on the internet. That means that we should have facilities for concurrent access. Right? Multiple users should be capable of simultaneously accessing the data in the database. Well, for this, DBMSs will include facilities for concurrency control to ensure that no conflicting operations are executed. Imagine that you have a database application in which you have a bottle of wine. You only have one particular bottle of wine. You put it on eBay, so multiple users can actually simultaneously access the bottle of wine. But as soon as one user makes the purchase, the bottle of wine is no longer available to the other users. So you have to make sure that only one user can make the purchase and not two people purchase that one bottle of wine, because that's simply not possible. So in order to achieve that successfully, the DBMS needs to have facilities for concurrency control. In a file-based approach, this becomes a lot more complicated. In the file-based approach, it is nearly impossible to have people or applications working on the same file. those facilities for concurrency control are not available. So, in a nutshell, DBMSs have catalogs. This is not available in a file-based approach. DBMSs or databases have program data independence. In a file-based approach, you have program data dependence. In a database approach, you can have the idea of views, which you do not have in the file-based approach. In a database approach, you have facilities for concurrency control, which you do not have in the file-based approach. Here you can see the DBMS or the database approach to data management again visualized with our previous example. So we have an invoicing application, we have a CRM application, customer relationship management application, we have a GIS application. All of them are going to work by means of the DBMS software, which is going to include both raw data and a catalog. Remember, the catalog contains all the metadata. So it contains all the data about the data descriptions, the constraints, and so on. And the catalog is one of the key differences between a database approach to data management and a file-based approach to data management. In what follows, we're going to zoom into some of the elements of a database system. First, we're going to talk about data models. Then we're going to talk about schemes and instances. We're going to extensively outline the tree scheme architecture. We're going to talk about data dictionaries. A data dictionary, also referred to as a catalog. So data dictionary and catalog are synonyms. And then we're going to discuss about DBMS languages. Data models are very important in this course. Basically, in subsequent chapters, we're going to discuss different types of data models. And what's a data model? A data model is a collection of concepts that can be used to describe the structure of a database, the data types, relationships, and constraints. Let's illustrate this with an example, again with the university application. So there we have the different types of concepts. So we have a student concept, we have a professor concept, we have a course concept, we have a building concept. And we're going to discuss those concepts and model what kind of information we want to gather about each of those concepts. So for a student, we want to gather student number, we want to gather student name, student address, student gender, etc. For course, we want to gather course number, course name, study points, etc. We're also going to discuss the data types. The data types are how the information should be represented. Student number is an integer. Student name is a string. Student email address also has a particular data type. So it's just like a set of characters followed by an @ sign, followed by a set of characters, followed by a dot, and then ending in com.be, whatever. You also have relationships which you're going to capture in your data model. So students can take courses. Courses can be followed by students. Professors can teach courses. Courses can be taught by professors. And you also have constraints. A professor should teach at least one course. It's a constraint. A course should be taught by at least one professor. That's a constraint. A student should take at least 60 study points or courses during an academic year. That's a constraint. So all those information elements, together with the data types, the relationships, and the constraints, should be appropriately captured in the data model. Data modeling will be a key activity in this course. And a data model is typically something which is being made between a business analyst or a business user, I would say, let's call it a business user, and a data modeler. The business user is the person that is going to use the database application and that understands the business problem. The data modeler is the person which is going to make the data model and that he or she wants to understand the business problem to make sure that the data model is as accurately as possible a reflection of the underlying business problem. You want to capture the information needs as accurately as possible. And there exist different types of data models. The first type of data model is a conceptual data model. Conceptual data model is a high-level model. High level, that means it's very user-friendly. It is not very specifically oriented towards implementation. So it contains high-level concepts. It has a representation of part of the reality, and it's close to how the user perceives the data. Types of data models, well, we have the EER model, that stands for Enhanced Entity Relationship Model. We're going to extensively comment on that in due course. And object-oriented models. These are two examples of conceptual data models that we're going to come back to. Next to that, you also have data models, which are going to be more implementation focused. Here we're going to discuss concepts that may be understood by end users, but are not too far removed from the physical data organization. So we're getting closer and closer to the implementation here. They're going to hide some details of data storage, but can be implemented on a computer system in a direct way. So those models are technically a little bit more detailed than the conceptual data models, which are more high level. Examples of implementation data models are the hierarchical model, the network model, the relational model, and the ODMG model, which we're again going to come back to later on. The physical data model is then really the lowest you can go in terms of implementation, because here we're going to have a low-level model that is going to describe the concepts and the data's physical storage details. Here we're really going to describe how the data should be physically organized. And the way you're going to do data modeling typically is that you're going to start from a conceptual data model, very high level, and you're going to make it more and more implementation specific. You're going to make it more and more specific to the physical environment until you end up with a physical data model. Also very important is the concept of schemes, instances, and a database state. In every database application, it is very important to distinguish between the description of the data, the metadata, the data definitions, the data structures, constraints, etc., and the data itself. A database scheme is a description of the database. So it's basically the metadata. It describes the data structures, the connections between them, and so on. And typically, this is specified during database design and is not expected to change too frequently. So here, we're again talking about those data definitions like professor, students, course, building, the relationships between them, and all the data items that we want to capture about them, student number, name, etc. All of that needs to be specified during database design, typically in collaboration between the business user and the data modeler. And once both of them have agreed upon those definitions, we will store them in the catalog. Remember, the catalog is a very essential part of the database approach towards data management. So this is the database scheme. The database state is then the data in the database at a particular moment, which is also called the current set of instances, the current set of observations. It's the data currently in the database. So let's just illustrate that. Here you can see a database scheme. You can see some data definitions. So we have a student information concept, which has number, name, address, email, course, number, name, and building number and address. Now, this is something which is going to be static. That means that it's not going to change too frequently. It may change. For example, at some point, you also want to include the student's Facebook account or student's Twitter account or LinkedIn account in the database, but it's not, those changes will not occur quite often, every now and then. Here you can see the database state. The database state means the status of the database at a particular moment in time. So you can see a student table with particular students in there. You can see a course table with particular courses in there. You can see a building table with all the buildings in there. This is going to be a lot more volatile in terms of content. So when a new student gets registered, you need to add them to the student table. When a student is going to change address, you need to change it in the student table. When a course gets removed, since it's no longer offered, you need to remove it from the course table. So you see, this is going to contain information that is a lot more volatile. A lot more volatile when compared to the database scheme. The database scheme, data definitions, are typically considered to be very static, whereas a database scheme, database state, is going to be very volatile. A very important architecture underlying any database application is the tree scheme architecture. Here you can see the tree scheme architecture visualized. We're going to start at the middle. The middle is the conceptual scheme. This is going to involve all the concepts about which we want to gather information. So here you have those concepts like student, you have the concepts like professor, building, and course. And there you're going to model all these concepts. You're going to say what information we want to gather about students, what information we want to gather about courses, what information we want to gather about buildings, and what are the relationships between them. Okay, that's the conceptual model. Now that model needs to be physically implemented at some point. At some point you want to have an internal scheme. Internal means a physical scheme which is going to discuss the physical implementation of that model. So some information may be stored in files, some information may be stored on disk or in the cloud. So you have different ways of physically storing the information. And basically what you want is you want to have physical data independence here. That means both layers, the conceptual layer and the physical layer, should be as independent as possible, such that if you make a change to the physical layer, it should have no impact on the conceptual layer. The external layer gives us the views. Now, what is a view again? Well, a view is a subset of the information in the conceptual level, tailored towards the needs of a particular set of users and or applications. You can have one view which offers you information tailored towards the needs of professors. Another view which is going to offer you information tailored towards the needs of students, and another view which is going to offer information tailored towards the needs of educational programming.